Welcome to College Algebra. In this lecture video, we're going to begin to talk about Chapter 10, Systems of Linear Equations in the Matrix Operations. Okay, so in this video, I'm going to talk to you a little bit about how we can use the idea of a matrices to solve our system of linear equations. Okay, so as you can recall, a system of linear equations is when we solve linear equations involving with more than one variable. So for example, if I got two variables, okay, and I want to solve for x and y, I will need two equations. Okay, so if I want to solve for x, y, and z, then I will need three different equations involving with x, y, and z. So together, this is called a system, okay, of linear equations. All right, so here I'm gonna just type it out, the ways, okay, to solve system linear equation. Okay, so in Algebra 2 classes, you probably heard something called the substitution methods. You probably heard something called the elimination methods. Okay, you probably learn how to graph your linear equations, okay, and see where the two straight lines intersecting. Okay, so you can do it by graphing. All right, there is actually other ways to go about solving system linear equations. One of them is actually going to be using matrix, and another way is actually using matrix but using something called the Cramer's rule. Okay, I'm actually not gonna go through, okay, in detail of the Cramer's rule. Okay, instead of what we're gonna do is using our matrices to help us to solve the system of linear equation. All right, so another way to solve such equation above is called the matrix. Okay, we can rewrite the above system of equations as the matrix of 2, -3, 7. These numbers come from the coefficients and the constant term of my equation. So we kind of line them up by the variable. So the 2 and the 1 are the coefficient for the variable x. So that means my first column are the variable x, the second column are the variable y, and my third column here, 7 and -2, okay, was on the other side of the equal sign. So technically there's actually a dash line that goes right here. Okay, there's a dash line goes right here that we do not enter into the matrix, okay, but it's there. All right, now when we write our system linear equation in the matrix this way, it's called an augmented matrix. Okay, another type of matrix is called a coefficient matrix, only contains the coefficients. Okay, it's called the coefficient matrix. We will use the coefficient matrix for the Cramer's rule here in a minute. Okay, or we'll use the coefficient matrix. All right, so the way how we read matrix is go by rows and columns. Okay, so the order of the matrix is called n by n. How many rows by how many columns? So for my matrix I wrote up here, which is coming from this system, that is a 2 excuse me, 2 row by 3 column. Oh Lord, my line is still okay. 2 row by 3 column matrix. Okay, so this one would be called a square matrix because it's 2 rows by 2 columns. Okay, now the entry, let's look at this coefficient matrix right here. The 2 is located at, okay, first row and first column. So that 2, okay, we're using the abbreviation of A because sometimes I can call my matrix A. Something called the AIJ entry. I stand for which row, J stand for which column. So my AIJ for my 2, that would be what? That would be 1 1 position. Okay. First row, first column. Okay. So if you ever see the notation AIJ, it's referring to which row, the entry of which row and which column. So the -3 is located at first row, second column. So that will be 1 2 entry. Alright, so for example, let my matrix C to equal to this. What is my order of my matrix C? So my order is 2 rows by 3 columns. Alright, determine the value of C of 2 3 entry. Okay, second row, third entry. Second row, third column. That will be the 5. Alright, where is C11? First row, first column. That will be my 6. First row, first column entry is my 6. Okay, so why am I using C? Because I call my matrix C. So that will be C of IJ entry. First row, first column is my answer 6. Okay, that's the way how we're gonna see it on the calculator. Alright, construct an augmented matrix correspond to the following system equation. So this system equation consists of 3 different variables. So it's kind of messy right now, so let's clean this up. So for augmented matrix, we want all the variables on the left side of the equal sign, and all the variable kind of line up together. So for this one here, I'm gonna multiply every term by 2. So that give me a 12x plus, if I times this middle term by 2, that would just be 5y minus z equal to, if I times this third term by 2, that would be 10. Alright, the second equation here, if I do a distribution and kind of clean this up a little bit, move my -7 over, that will be positive 12. Okay, 3 times -6x, -18x. Alright, 3 times 5z, that'll be positive 15z. And my positive y still positive 1y. Alright, my third equation, x is x. Alright, move my positive 4y over to the left side of the equal sign, that will be -4y. -1 times positive z, negative z, stay on the left. -1 times 7 is -7, move it to the right hand side, that will be positive 7. So my augmented matrix, my first row, or my first equation, that will be 12, 5, -1, and 10. My second row, -18, positive 1, 15, and 12. Alright, my third row, 1, -4, -1, and 7. Okay, so this is a 3 row by 4 column. So these numbers, so when you say augmented matrix, these last column is what's on the other side of the equal sign. Okay, alright, so how can I use matrix to help me solve system linear equation? So to solve system linear equation is the same thing as reduce the matrix to its simplest form. That's called the row reduced echelon form, RREF. Okay, so once we perform the row reduced echelon form, once we write them in that form, we can actually easily read the solution. Okay, so I'm gonna do this in the calculator. Okay, rather than show you how to do it by hand, I will enter my augmented matrix in the graphing calculator, so we can actually perform row reduced echelon form using the calculator. Now the result of the row reduced echelon form What I want to see ultimately is where the diagonal entries are all 1, okay, and my other entries are 0. So remember, if I'm using this example, okay, where I got 2 rows and 3 columns, 2 rows and 3 columns, I want my diagonal entry to be 1 and all the other entries are 0. Okay, so whatever is left in the third column, okay, will be my answer. Because when this first entry of the first row says 1, that means 1x is equal to this number. So the second row, when the second row, second column entry says 1, that's referring to 1y is equal to this answer. Okay, so normally when we read our answer, we read them from left to right. 1x plus 0y equal to this answer, 0x plus 1y equal to that answer. That's what I want to see. Okay, alright, so generally when we solving for system of linear equations, okay, we got 3 types of solutions where we can have 2 lines intersecting at 1 point. Okay, so that's referring to the system is consistent and the equations are independent from each other. Consistent means there is a solution. Okay, the equations are independent, that means they are different equations. They are, they don't depend on one another, because if it turns out the 2 equations are exactly the same, or when we graph it's called the same line, you actually have infinite number of solutions. Okay, where the system is still consistent because our solution is infinite, but the equations become dependent. Okay, dependent simply means that one equation depends on the other one. For them to be the same line, if one line changes, the other one also got to change. Now when we graph it where my 2 lines are parallel, that means I have no solution. Okay, where the system is inconsistent, equations are still independent. So 3 types of answer: intersect at 1 point, no solution, or infinite number of solutions. Okay, so I will show you what they look like here just in a minute when we read the matrix. Okay, so the homework has different actually to do it different ways, but I prefer you to enter in the augmented matrix, okay, and using graphing calculator to do this. So let's get started here. Okay, this is a 2 rows by 3 column. So in my graphing calculator, okay, the word matrix, second matrix, go to the word edit. Okay, choose the first matrix, that's fine. Press enter. Okay, my matrix is 2 rows, enter, 3 column, enter. Now we're just typing the typing our coefficients. So that will be, see that 1 1, that will be first row first column entry, which is my 7, -1, 43. Alright, press enter. Now jump to second row, -6, 7, and -86. Alright, press enter. Now it gets a little bit tricky. Now once I enter my matrix, I want to get out of this screen by pressing second quit, because that will take me back to my home screen. So now I go back into my matrix, highlight the word math, and go up until you see row reduced echelon form, RREF. Press enter. So now my calculator take me back to my home screen. Row reduced echelon form of who? So go back to the matrix again, select my number 1 under names, select number 1 because that's where I edit my matrix, and press enter. So this answer, okay, this answer demonstrates the diagonal entries are 1, everybody else are 0. So you read this as 1x plus 0y equal to 5. So that means x equal to 5. 0x plus 1y equal to -8. Because remember now, there's a dashed line here where the third column was on the other side of the equal sign. So the second row says y is equal to -8. There you go, intersecting at one point. So my answer, okay, my system is consistent. Okay. Now the problem says if the system is dependent, express the solution set in terms of one of the variables. Okay, so we can just write them out in terms of variables. I'll show you how to do that just in a minute when we see one. All right, let's look at this one on the right here. All right, this one is missing a x right here, so that will be 0x. So let's try this one. Second matrix, go to edit, choose the same one as I did already. So 2 by 3, so I press enter, 0x, enter, -5y, enter, -8, enter, -1, enter, -3, enter, and then 9, enter. Alright, once you enter them, press second, quit. Okay, then we say second matrix. Go back into matrix, highlight the word math, and look for B. Row reduce echelon form. And we go back into the matrix, and under the word name, select my matrix that I just edited, number 1, and here we go. Alright, convert this into a fraction, math, number 1. There you go, that's a little bit better. So now this answer means x equal -69/5, y equal to 8/5. That would be my answer. Okay, nice and easy, very simple. Alright, just by looking at this equation, okay, just by looking at this equation, if I divide my second equation by 5, that would be x minus 6y equal to -20. Okay, so the x, the y is all the same. Okay, well, on the other side the equal sign is different, so that tells me that this is either going to be parallel or going to be the same line. Alright, so let me show you what it looked like. So let's go back to our matrix and enter these answers, and enter these number coefficients. 2 by 3 again. 1, -6, -19, enter. 5, -30, -100. Okay, second quit, second matrix. Okay, looking for B. So I know the alpha B. Go back to the matrix, choose number 1. Alright, so here we go. Right here. Diagonal entry got to be 1, but here my diagonal entry is not 1. This one says 0. So if you read the second one, it does say 0x plus 0y equal to 1. Does 0x plus 0y equal to 1? No. Alright, when that happens, okay, when that happens, that means it has no solution. Okay, it has no solution. If the system is dependent, okay, express the solution, say, in terms of the one variable. Dependent is referring to the same line where we have infinite number of solutions. Right now I have no solution because I actually have parallel lines. If I graph these two equations, I actually end up with parallel lines. Okay, so this one have no solution. So when you see one row says 0, 0, and then on the other side equal sign there's a numerical value, that's actually saying there's no solution. Okay, because the two lines are parallel, they will never intersect. Alright, let's jump it up to 3 variables. Okay, So the problem is not enough to leave out the spaces. So those are the missing terms. So I will put in zeros for those. So this particular problem, where I got 3 rows by 1, 2, 3, 4 columns. This is a 3 by 4. Let's go edit this. Okay, 3 entered by 4. So 1, 6, 0, 22, 0, 1, negative 5, 9, negative 2, negative 3. Ooh, messed up. Let me go to it. Negative 2. Negative 3, 4, negative 4. Okay, let's make sure I got all my numbers. Okay, I think so. Alright, once I key it in, second quick, go back to my matrix. Under math, look for row reduced echelon form. Go back into matrix, select my matrix I just edited, which is my first one. Let me convert this. Math. Number 1, convert them to fraction. I think the whole one fraction. Oh, nasty. Okay. So it's over 49. Alright, so my answer, the point of intersection in this 3 dimension, because 3 variable means 3 dimension. X equal to that, Y equal to that, and Z equal to that. Okay, so that's the point of intersection between the 3 lines, or the 3 planes. That's what they call it. Okay, because 3 dimension is actually going to be planes. Alrighty, so one of these problems that we're going to try is where we're going to see either no solution, or it's going to be the same line. Okay, so we can kind of look at this and we'll probably tell. No, not really. I can't really tell. All right, let me just try one right here, real quick for you. So the process is very simple. Okay, how we solve it. Now there is a course in 4-year college called the linear algebra. In that course, they will actually teach you how to do all this stuff by hand. How to make your diagonal entry into 1 by substituting particular values, okay, and then switching the rows and columns so you can add and subtract them. But we're not going to focus on that here. We're just going to use technology to kind of help us to solve it. So if you're ever interested in taking the linear algebra course, okay, they will teach you how to do all that. -5. Here I want to show you what the solution looks like. In this particular 3 by 4. Okay, second quick, second matrix. Go to math. Row reduce echelon form. Go back into my matrix, select my name. Okay. No, not this one. This answer is very clean. Okay, so that's not that one. So let's try this last one right here. So this is your answer. X equal to -45, Y equal to 50, and Z equal to 11. So let me see, maybe it's this one. I do want to run into it. I thought I put one here. let's see. Second matrix, math. Second matrix, number 1. Here we go. Alright. Ooh, this is a good one. Alright, let me see if I can do this. Take a picture of that. Let me convert to a fraction first. Alright, here we go. Alright. So this answer is very strange, because the last row, so the previous one, the last row is 0x plus 0y equal to 1. This one says 0x plus 0y plus 0z is equal to 0. That is true. When the last row is not true, that's no solution. So when this last row is true, that means it's all real number. Okay? Because technically, what is my x and y? Okay? And z. It doesn't really tell you, because all the other answers tell you exactly what x is, what y is, what z is. This one doesn't really tell you. Okay, so when that happens, you actually have infinite number solution. That means these lines are actually the same line. Alright, so infinite solution is where equations are dependent on one another. So the problem says express the solution set in terms of one of the variables. Leave all fraction answer in fraction 4. So we can say this is either x plus z equal to 4/3, or we can say this is y minus z equal to negative 14 over 3. Okay, leave the solution set in terms of one of the variables. So you can either probably solving for z, okay, or you can solve for x or solving for y. Alright, to express your answer on the homework. But I want to show you what it looked like, okay, when you have infinite number solution. That's where the last row diagonal entry is no longer 1, okay, but the last row is actually all zeros. That's infinite number solutions. Alright, so in the next video I'm going to show you how to do some operations of matrix, and we're going to talk a little bit about Cramer's rule as well. Alright, thank you for watching.